All right, so dy dx. So let's draw that in our drawing here. Slope is rise over run. So these differentials we're talking about are on our tangent line. And we have this dy dx. And now what we're also going to do is we're going to be mapping some points on x. So let's call this dx, so going over to point R, we'll call that distance delta x for change in x. Okay, so we have a dx, which is the differential, and then the delta x, which is the change in x. Okay, and what we're going to do is we are going to map that onto our function, f. Okay, and now on our function, going from, we'll call this point Q on the function. So we have 3 points that are happening, okay? P is on the tangent and the curve, R is just on the tangent line, and Q is just on the function. And so what we're going to label the difference between Q and P on the curve, that's your delta x, and we're going to call this your delta y. All right, so some observations. Delta x and dx are the same. The differential dx and delta x, change in x, are the same. This whole distance going from P to R, that's dy, but then delta y is just the smaller distance, the vertical distance from P to Q. Okay, so let's write some of that stuff down. So delta y is the change of the curve, the vertical change of the curve f, and then dy is the rise of our tangent line. Okay, and then we're going to have a formula for delta y, the change in the curve. We are going from, we're looking at f of x plus delta x. Okay, so x plus delta x is here. So that puts us at point Q. And it's the distance, the vertical distance from Q to P. So minus f of x. Okay, so let's see how we're going to apply all of this stuff. Oh, and let's write one other thing. We can visually see it, but we can also see that dx is equal to delta x. So, all right, so let's see how we're going to use these differentials. And let's see why they're handy. So first, we're just going to get a feel for all of these definitions, and we're going to compute delta y, so change in y, and dy, the rise on the tangent, for y equals x minus x cubed. At x equals 0, and the change of x equal to negative 0.3. Okay, so let's draw a picture. So let's do a quick sketch of this y equals x minus x cubed. I'm going to write the leading coefficient first. Okay, so I'm just rearranging it. And the reason why I'm doing that is I want to get the basic shape. This is I was going to say an odd function, but it ends in an odd power, right? The degree is 3. So we know the ending behavior of a degree 3 function is this, right? Think, a linear function, the highest power is odd, the cubic, that's the end behavior, but it's negative, so it's flipped. So the end behavior of this function is going to look something like that. Okay. So I'm trying to just do a quick sketch so we can see what's going on here. In addition, we can also find out the y-intercepts. The y-intercept is 0. Y-intercept happens when x equals 0. So we definitely know there's going to be a 0, 0 here. And the x-intercepts happen when y is 0. Again, I'm just trying to get a quick sketch of this. We're not asked to do that, but sometimes it's just helpful to figure out what's going on with all these dy's and delta y's. All right, so looking at this, each of the things, if I wanted to get fancy, I can even factor it more. All right, so now we can figure out the zeros of the function. The zeros of the function can be when each one of these factors are zeros. So the x-intercepts are going to happen at 0, -1, and 1. Okay, so there you go. And then we're just doing a rough sketch. We also know the end behavior. We start up here, and we're going to end down here. And we're only going to cross the x and y axis at these points. So that's enough information to get us a quick little graph. Okay, so this is approximately what our graph is going to look like. And now we're interested at x equals 0 with delta x equal -0.3. So that could be your delta x, -0.3. And what we're doing in this section is we're creating these tangent lines. So we would be creating a tangent line at 0, something like that. Okay, because it says x equals 0. And now delta x is -0.3. So we want to find delta y and dy. All right, so first of all, the delta y is going to be the vertical change on the curve. So it's going to be this distance. That's going to be your delta y. And now dy is going to go all the way to the tangent line. And that distance, that's going to be your dy. So that's what we're finding. First, we have to find delta y, the vertical change on the curve, and then we're going to find dy, the rise on the tangent line. Okay? All right. So now that we have a visual of what's going on, let's use some of our formulas. So we have a formula for delta y. So that's what we're going to use for delta y. Then we also have a formula for dy. So this is what we're going to do. And we're going to discover something at the end of this, because you're probably wondering right now, why are we doing all this? And we're going to discover. Okay, so delta y. So we're going to do this little part right here. Delta y is going to be x plus delta minus f of x. All right. Again, that's this formula right here, where x is 0 and delta x is -0.3. Okay, so we're going to plug in -0.3 to our function right here. Actually, we can go back to the original one. This is our function. We're going to plug in -0.3. Okay, and now f of 0 is just going to be 0, so -0. All right, so throw that in the calculator. And we're going to get -0.273. Okay, so there you go. And that's what your delta y is. Put that in a little box. Okay, and now we want to find dy. And remember, dy is f prime of x dx. That's your differential. Well, what is f prime of x? It's going to be, let's see, y prime is going to be 1 minus 3x squared. 1 minus 3x squared. I'll just write that like here. So 1 minus 3x squared, write that better, dx. All right, and now what's x? X is 0. So it's going to be 1. And then what was dx again? Let's go back up here. Well, delta x was negative 0.3. But we saw that delta x and dx are the same thing, right? Because this is delta x and this is dx. So if delta x is negative 0.3, that means dx is also negative 0.3. Okay, so then 1 times it is negative 0.3. All right, so we have then that dy is negative 0.3. Okay, so which one is easier to calculate? Which one could we instantly do in our heads and not have to use a calculator? This one right here. This was easier to calculate. And that's the point of this section. Linear approximations can approximate values on the curve, and that's good because it's easier. Lines are just easier to work with. And so here's what we've done. We can use dy, the vertical distance on the tangent, to approximate the vertical distance on the on the curve. And dy is an approximation of delta y, and dy is easier to calculate. So that's the moral of the story. We can calculate a change. We can calculate a change easier on the tangent line. Okay, so this is going to lead us here. So alternative linear approximation method. So alternative linear approximation method. Okay, so first of all, let's recall some of the work we've done in this section. We can approximate our function by using the tangent line. This is the formula for the tangent line at A. All right, when x is fairly close to A. So in differentials, what we were just looking at, f of A plus dx is approximately f of A plus dy. That's what we were just looking at. So let's look at a picture. We'll go back to that example we were just looking at. F of A, right? This is like f of 0 plus dx. Okay, it would be this value right here on the curve. But we can approximate that looking at f of A plus dy. All right, so there we go. So let's look at an example that we did at the beginning of this section. We looked at g of x equals the cubed root of 1 plus x, and we found the linear approximation, and we were able to estimate the cubed root of 0.95 to be approximately 0.9833. Okay, so now what we're going to do is we're going to use differentials. And we know that dy is equal to g prime of x dx. All right, and that's what we were just practicing up here. We were practicing finding dy. So if we have dy, then we can use this formula. So that's where we're going with this. Okay, so let's keep going. dy. G prime of x, remember we can think of g as 1 plus x to the 1/3 power. So let's take the derivative of that. Okay, and of course I like to clean it up. It just looks nicer. Okay, and then in this scenario that we had up here, let's remember that we let x be 0, and we let the change delta x, but remember delta x and dx are the same thing, and we said it was equal to negative 0.05, okay, because that's how we're going to get down to 0.95. All right, so this stuff was already established in the previous example. Okay, so if we plug everything in, okay, remember x is 0, so, whoops, this should be a positive 2/3. 1 to the 2/3 is just 1, so I'm just going to write this as 1/3. And then dx is negative 0.05. Okay, so then using differentials, multi-step problem, we have this, the cubed root of 0.95. We can write it like this, g of 0 minus 0.05. Let me show you why. I'm matching this notation, 0 plus or minus 0.05. So it's going to be f of 0 plus the dy we just found. So g of 0 plus dy. Okay, that's going to be 1 minus 0.05 over 3. And then that is going to be the 0.98333333, okay, which is what we got last time. So a different way of looking at the same problem, right? We're doing the exact same thing, we're just looking at it differently. Last time we created the tangent line around x equals 0, and then estimated our new value of x, that negative 0.05 on the tangent line. This time we're using our differentials. Okay, so excellent. So now we should be fairly comfortable in using the tangent line to estimate values on the function close to a. And now we know the motivation behind it. It's easier to calculate values on the tangent line versus the curve of the function in some situations. And so now we're going to look at some applications. So our first application, or the application we're going to do together, is going to be number 35 in the homework section. And this is what it has. We have the circumference of a sphere. I always like to draw pictures. So the circumference, the distance around the sphere, is 84 centimeters. Okay, and we know that when we're measuring things in real life, there's always a chance for error, right? There's always a rounding error, maybe there's a user error, something like that. And in this problem, it says there's a possible error of measuring this circumference